Today I want to talk about how to use the law of signs when we have something called the ambiguous case. So the ambiguous case comes up when we have a side length, or two side lengths rather, and a non-included angle. So for example, you have something like this first scenario. You know an angle A, that we'll call capital A, and the side adjacent to it, and then you also know the side opposite to the given angle. So we call this situation SSA, or you might remember it from geometry as the bad word, angle side side, or ASS. Yikes. So if you remember from geometry, that was not a way to prove triangles are congruent. You could not prove triangles are congruent using ASS or SSA. And yes, I know I just wrote the bad word. Couldn't prove triangles congruent using that postulate or theorem. But that's all because of something called the ambiguous case, which we're going to discuss today. Let's discuss this triangle first. So it doesn't really matter what this angle is right now. We can call it some acute angle here, let's say 40 degrees. And then this red side is 5, we can call it centimeters, inches, doesn't really matter. And then the side opposite that 40-degree angle A is 8 units in length. So in this first scenario, you'll notice that the side opposite the given angle, which is side length A, you notice that side length A is greater than side length B. So in this situation, there's only one triangle that can be drawn with these given side lengths and this given angle. So this situation is not ambiguous because the side opposite the given angle is longer than the side adjacent to the given angle. But what if that's not the case? What if we have something like this, where it's still the same angle measure, A, but now we're changing the lengths of the sides. Now the side adjacent to that angle is 8 units, and the side opposite that angle is 6.5 units. So now notice the side opposite the given angle is no longer than the adjacent side. So now you'll notice that if this dashed yellow line is the height of the triangle, we know it's the height of the triangle because it's the perpendicular segment running from a vertex to the base. And as you can see, let's pretend this is drawn perfectly to scale. This side length A is longer than that height of the triangle, but it's shorter than side B. So side A is in between the lengths of the height of the triangle and the adjacent side, or the side next to the given angle. So that's one possible triangle with that given angle and those two side lengths. But what if we actually, in the very top of this triangle, we considered it like a hinge? What if we took that side length A and we rotated it to the left, like that, past the height segment, and we planted it right here? So then that new blue segment you can see is still the same length. It's still 6.5, and the red segment didn't change. It's still 8 units in length for side length B, and that angle measure didn't change. It's still the same angle. So now we've drawn two different triangles that have the given measurements. Both of these triangles have angle A, the side adjacent to angle A as 8 units, and the side opposite angle A as 6.5 units. So whenever the side opposite the given angle is greater than the height of the triangle, but less than the side adjacent to the given angle, we have this two triangle situation, which makes it a little more complicated to use law of signs to solve for missing sides and angles. So we'll do some examples of how this plays out in a second. But let's talk about the last scenario. So the last scenario, we still are given this angle A and the side adjacent to angle A, and we're calling that side length B. But now the side opposite the given angle, which we're calling side length A, notice that that side of the triangle is much shorter than the height of the triangle. And so there's no possible way for this short little side, which is smaller than the height, there's no possible way to form a triangle here. We can't connect these vertices of the triangle to form a triangle. So this happens whenever we have a side opposite to the given angle, so side A, whenever that's smaller than the height, and then the height of the triangle is always smaller than the side adjacent. So whenever this happens, we actually have no triangle. I realized I should probably talk about one more case, and this is when you're still given angle, adjacent side, side opposite, but now you know that the side opposite the given angle A, now you know that that side is the same length as the height or that perpendicular segment of the triangle. And when this is the case, as you might imagine, this means that you have a right triangle because that segment is also perpendicular to the base, and there is only one way to draw that triangle. So there's one right triangle created when the side opposite the given angle is congruent to the height of the triangle. All right, so example 1. We're given two sides and a non-included angle. So we're given this 30-degree angle measure for angle A. We're given that the side adjacent to that, side B, is 16 units. And then the side across from the given angle is 7 units. And the question's asking for us to find the measure of angle B. Before we can do that, we want to think about the ambiguous case, because we do know that we have an SSA situation going on. So whenever that happens, we want to think about, all right, do we have a possible triangle at all, or is there 0 triangles that exist? Or is there one triangle that exists, or are there 2 different possible triangles that can be drawn giving these measurements here? So remember, it really matters how these different sides compare, side B and side A. Obviously, side A is smaller than side B, but for a triangle to exist, then side A is going to have to be longer, or at least equal to, the height of the triangle. So how can we find the height of this triangle? Well, we can think about how if it's a height, then it's making a 90-degree angle with the base of that triangle, which means that we have a right triangle right here. And so what can we do with right triangles? Well, we can use SOHCAHTOA. Side B is the hypotenuse of that right triangle. So to find side length H, which is the opposite side, we want to use the trig ratio that involves the hypotenuse and the opposite side, and that's sine. So sine of 30 degrees, we know that's equal to opposite over hypotenuse, so it's equal to the height over 16. And so then to solve for h, we just multiply 16 times sine of 30. And we get the height is equal to 8 units. So this does mean that side length A is smaller than the height of the triangle, which is smaller than B. And whenever the side opposite the given angle in this situation is shorter than the height of the triangle, we know that we have no triangle that exists. Which means that we can't solve for measure of angle B, because it's not a true triangle. I do want to take a second to show y'all what happens if you do try to solve for the measure of angle B using law of sines here. So remember, we use law of sines when we have, we're trying to find a missing side or a missing angle, and we know one pair of angle and opposite side. So that's our pair that's known. And then we're going to use this second pair in the law of sines to solve for the measurement of angle B. So remember from last lesson, and if you haven't watched last lesson, this will not make sense. So please pause this video and go back to the last lesson to get a nice intro to law of sines. But the law of sines allows us to write sine of angle A over side length A has to be equal to sine of angle B over side length B. So now substituting everything in, we're going to write this as sine of 30 degrees, because that's angle A, over the length of side A, which is 7. That's equal to sine of angle B, and we don't know the measure of angle B yet. That's what we're going to solve for. And then over side length B, which is 16. So then we're just going to cross multiply, so we get 7 times sine over B equals 16 times sine over 30. So we have to divide both sides by 7. So sine of angle B equals 16 times sine of 30 degrees divided by 7. And we know from last unit that to solve for the measurement of angle B, or to solve for B, we're going to have to take sine inverse of both sides. And so we are left with measurement of angle B equals sine inverse of that whole expression above. So we're just plugging that in into sine inverse in our calculator. And this expression here, it's about equal to 1.143. And from last unit, you guys remember that the domain of sine inverse has to be between -1 and +1. So if you actually entered this whole thing in your calculator, you are going to get a domain error because we have a sine value that's greater than 1. So it makes sense that we're getting a domain error and we can't solve for the measurement of angle B here using our calculator, and that's all because no triangle exists in the first place, because the side opposite the given angle is shorter than the height of the triangle. So here's another scenario. Now we are given an angle of 30 degrees. The side adjacent to that angle, B, that is 16 units in length. The side opposite to that given angle, which we're calling A, that's 20 units in length. So this is a different situation because now the side opposite the given angle is actually longer than the side adjacent to the given angle. So when this situation happens, we don't even need to think about the height of the triangle. We already know that when we have a side opposite the given angle longer than the side adjacent to the given angle, we already know that only one triangle exists. And this is just something that you guys can memorize. So side opposite greater than side adjacent. That means one triangle exists. And now we are going to solve for the measure of angle B, which we couldn't have done in the last example. So this problem could have been out of lesson 1. We are still going to use the law of sines here, and we only have to use the law of sines for one triangle. So let's see. Sine of 30 degrees over side length A, which is 20 units. That's equal to sine of angle B over the length of side B, which is 16 units. We cross multiply. And divide both sides by 20. So we get sine of angle B equals 16 times sine of 30 degrees over 20. And so again, we are going to take sine inverse of both sides to solve for the measurement of angle B. And so that's equal to sine inverse of 16 times sine of 30 degrees all over 20. So now take a moment, make sure you guys do know how to enter this correctly in your calculator. You also need to be making sure that your calculator is in degrees mode. So sine inverse of 16 times sine of 30, and divide that amount by 20, and you get 23.58 degrees. And it's a good idea to always think about, well, does this make sense? We know that sides grow in proportional to the angles opposite them. So the larger the angle, the larger the side opposite. So since side A is 20, we do expect angle A to be a larger angle than the angle opposite the shorter side, side B. And so that's exactly what's happening here. We're getting this measure of angle B is 23.58 degrees. And so that makes sense. I don't want to make this video too long, so I'm not going to show the rest of the work you would need to do to solve the whole triangle, like find the measurement of angle C and find side length C. But you could do that. You could think, oh, all right, I know that these three angles within the triangle, they add up to 180. So you can subtract the measurement of angle A and the measurement of angle B from 180 to get the measurement of angle C. And then once you know that, you can use law of sines like you learned in the first lesson to solve for side length C. So feel free to pause the video and take the time to do that. But I'm going to move on to the next example so this video is not too lengthy. All right, now for the big kahuna, the situation when two triangles exist. So you might not necessarily know right off the bat if I didn't tell you that two triangles could exist here, because I'm not going to draw that dashed line in for you guys on like homeworks and quizzes and stuff. But if these were the given angle, side, and side that were given to you in a problem, you're first going to think about, all right, well, I know that the side opposite the given angle is not larger than the side adjacent, so I know that not just one triangle can exist. So I want to think about, well, is there 0 triangles that exist, or are there 2 triangles that exist? And that's all based on the relationship of this length to the height of the triangle. So first we need to think about what the height of this triangle is going to be. So you guys can solve for that using SOHCAHTOA, since it's a right triangle that's being created with that height segment. Or you guys might remember that this is going to be a 30, 60, 90 degree triangle. Since this angle here is 30 degrees, this angle is 90. I know this full angle in here has to be 60 degrees. And so I know that the hypotenuse is going to be twice the length of that short leg. So I know that that short leg, which is always the side opposite the 30-degree angle, I know that that side has to be half the length of the hypotenuse. And so if that height there is 8 units in length, then we do have 2 triangles that exist because A is greater than the height of the triangle, but it is less than the side that is adjacent to the given angle. And this means 2 triangles exist. And you guys can kind of see, I'll erase the height now because that's all we needed that for. You guys can kind of see that the two different triangles that could be created there. So we have that side, that's 10 units, side A, but it doesn't necessarily have to be coming out from that angle from side B. We could just make this a hinge and move this side, rotate it towards the given angle, and make it this segment that I dotted in. And this triangle here has the same given information. This triangle, which I'll highlight in green, this triangle here still has a side that's a side adjacent that's 16 units, a side opposite that's still A, it's still 10 units in length, and the given angle of 30 degrees. So that full red larger triangle can exist, or that green smaller triangle can exist. And notice that green smaller triangle is actually going to be an obtuse triangle. This angle down here is an obtuse angle. So we are going to solve these two triangles separately now, and I'm not going to lie to you guys, this is very complicated stuff and is just super confusing for students at first. So I do hope that you guys will have patience with yourselves as you're learning this for the first time, and these problems can be pretty tedious and lengthy. All right, but this first triangle, so this triangle, the smaller green obtuse triangle, we know that it has a 30-degree angle, a side length B that's 16, a side length A that's 10 units, and that angle 30 is angle A. And then that obtuse angle is angle B, because that's the angle that's opposite side length B. So that top angle is angle C. So we are still going to use law of sines to solve for the missing angles and side lengths in this triangle. So we can think about the pair of opposite angle and side. So this side opposite the 30-degree angle, that's one pair, and we're going to use this other pair to solve for the measure of angle B. So sine of 30 degrees over the side opposite it, which is 10, that's equal to sine of B over 16. We cross multiply, and we get 10 times sine of B on the right-hand side. We're going to divide both sides by 10, so we get sine of B. I don't know why I switched the sides of the expressions. I didn't need to do that. All right, so we're going to put all of that into our calculator and then take sine inverse of that. And so the measurement of B is equal to sine inverse of that whole expression in there. When we put that in our calculator, we get 53.13 degrees. But that doesn't make sense, right? We know that this angle that we're going to be calling angle B, or that's the same thing as this angle here, we know that that's going to be an obtuse angle. So what our calculator just gave you, or what our calculator just gave us, is this angle over here. It gave us the angle of the red triangle. That's the angle opposite side length B in the red triangle. So that 53.13 degrees, that is actually this angle here. And so now let's think about Well, how does that help us find the obtuse angle? Well, we know that this triangle here, so not the red triangle or the green triangle, but this triangle that I'm outlining here, what kind of triangle is that? Hopefully you guys think isosceles because the triangle has two congruent sides. These two sides coming up from the base, they're both 10 units in length. So in an isosceles triangle, you guys might have remembered from geometry that there's also going to be a pair of congruent angles. These are called the base angles of an isosceles triangle. So if that angle is 53.13 degrees, then the other angle is also 53.13 degrees. And so then we know the angle that we were really trying to solve for, angle B in the green triangle, we know that that angle is going to be 180 degrees minus 53.13. So let's call, just to make everything super clear, we are going to call this angle B, 53.13 degrees is the measurement of angle B. And then that obtuse angle that we can now find, we're going to call that B prime. So the measurement of B prime is 180 degrees minus 53.13 degrees. We know that these two angles here, we know that they're supplementary, they're forming a straight line. And so if this angle is 53.13, then this angle would be 180 minus that angle. And so when we put that into our calculator, we get the measurement of B prime, which I notice now that I still wrote as B. Measurement of B prime is approximately equal to 126.87 degrees. So that angle in there. And so from there we can find the measurement of angle C prime. We're going to call that C prime, so then we can still reserve the big angle C. So this whole angle here, we'll call that angle C, and then that tiny sliver, angle C prime. And we know that the interior angles of a triangle add up to 180. So the measurement of C prime, let me still write in green so it makes sense which triangle I'm talking about. Measurement of angle C prime, that's equal to 180 minus 126.87 minus 30 degrees. And so we get 23.13 degrees for C prime. And you can also find the measurement of angle C. So this angle up here, you know that the measurement of angle B is 53.13. You know the measurement of angle A is 30 degrees. So you can find the measurement of angle C by subtracting both of those measures from 180 degrees. And when you put that in your calculator, you get 96.87 degrees. So again, for the sake of time, I'm not going to show how to solve for the remaining side lengths you need to know, but you can just use law of sines like usual. So to solve for this small side of the green triangle, you can use law of sines using the measurement of angle C prime that we now know. And to solve for the full length of C in the red triangle, Again, you can use law of sines using the measurement of angle C that we just solved for. So again, feel free to take the time to do that, but next class I'll show like a full worked out example for when two triangles exist.